Hey everybody, Mr. Anderson here. Welcome back to another edition in geometry. Today we're in chapter 8. We're starting chapter 8 and I've split it up today into two parts, 8.1a and 8.1b. So today we're just going to do 8.1a, which is simplifying radicals and then the geometric mean. We'll talk more about the geometric mean in 8.1b. All right, so for today our objectives are going to be simplify radicals and radical expressions using the product property of radicals, and then we'll find the geometric mean between two numbers. Okay? All right, so first of all, a radical, again, remember kind of what a radical is. A radical expression contains a radical, which a radical, you could think of that as a square root, could be a cubed root or something like that as well, but for our purposes right now, square root. The radicand, if you remember, that's what's underneath the radical sign. Okay, and so what we're going to talk about today is the simplest form. Okay, there's a couple of rules about the simplest form of a radical that you want to put it in. Number one, you don't want a radicand to have any other perfect square factors other than 1. So if you can take what's under the square root and get a perfect square out of that, you're going to do that. Okay, that's what we're going to talk about today. You don't want any of the radicands to contain fractions. I'm not going to talk about that today. We don't really need to, but in my Algebra 2, I think 6.5 video, I think I'll talk about that. And then also, the other thing is you don't want any radicands to appear in the denominator of a fraction. So you don't want any square roots in the bottom of a fraction. As well, and again, not going to talk about that today, but I just wanted to review the rules. We're really just going to talk about part 1 today. Okay, so here's the product property of square roots. Basically, what it says here is whatever's under the square root. To try to clean this up for you, whatever's under the square root, you can split it up through multiplication. So, example here. They say the square root of AB could be written as the square root of A times the square root of B. Okay? And again, these if A and B are positive. So for example here, they break this down. They say, well, they kind of maybe do this a little backwards from what I would think. Well, actually, this is a pretty simple example here. But notice if you have the square root of 4 times the square root of 9, well, 9 times 4 is 36. So you could say, oh, the square root of 36 is 6. But if you did each of these separately as well, say you did the square root of 4 times the square root of 9, what's the square root of 4? 2. Square root of 9 is 3. And so guess what? That also equals 6. So as you can see, we could just take square root of 36 and equal 6. Or if I broke it down into 9 and 4, together those will make 6 as well. Okay? So that's what's happening here. So let's take a look at an example here. All right, square root of 52. Now this is not going to break down evenly like that first thing, but what I'm going to try to do, and there's maybe two ways to look at this. Again, remember we want to take out all of the perfect squares that we can. So remember perfect squares that you have. You've got the square root of 4 equals 2. You have the square root of 9 equals 3. Square root of 16 equals 4. Square root of 25 equals 5, 36 equals 6, square root of 49 equals 7, square root of 64. You're probably not going to need to go much higher than this, but square root of 81 equals 9, and then of course square root of 100 equals 10. So one of the ways that you can think about this is see if you could take 52 and divide it by any one of these numbers because these are perfect squares. And so in this case, this may not be one that's really noticeable or obvious, but what you could do is you could take 52 and divide it by 4. And that comes out evenly. And so what happens is if you split this up, you could split it up into square root of 4 times the square root of 13. And then you say, oh, the square root of 4 is 2. So this would end up being 2 times the square root of 13. That would be the simplified version because we had a perfect square inside of 52 that we wanted to take out. The other way that you could do this, sometimes it's easier, just break it down into all its prime factors. So you might not notice 4 right away, but you'd probably say, hey, 52 can be divided by 2, so 2 and 26. Now neither of those are perfect squares, but 26 we can break down again to 2 and 13. And now you notice if you look at the prime factors, so to speak, of 52, you got 2, 2, and square root of 13. Well, the square root of 2 times the square root of 2 is just 2, right? Because remember, anytime you take the square root of 2 times itself, you're squaring it. And remember, if you raise something to the second power, that will undo or cancel out the square root. So if you have 2 of the same factor, it just comes out as a 2. And then, of course, you got 2 square root of 13, which is the same thing. One way that you could maybe look at this is, I've heard this said before, that you know, if you think of the square root as being like in the house, in order to get out of the house or get outside of the square root there, you have to have a date. And so notice here, 2 and 2, they had the 2, there were 2 2s, so they had a date, and so they got to go out of the house together as a regular 2. So, you know, whatever. All right, let's look at another one. Square root of 45. This one, to me, is a little bit more obvious because I think, oh, you know, square root of 45 could be broken down to square root of 9. 9 times 5 is 45. And now in this case, you go, well, square root of 9, that just breaks down to 3. So you got 3 square root of 5. Again, if you want to think about getting out of the house to go on a date, the square root of 9 would break down into square root of 3 times square root of 3. Guess what? They've got a date, and they can come outside of the house. Now they're outside together. And, of course, 5 didn't have a date, so he had to stay at home. Oh, well. Now, the other thing that can happen here as well is you might be able to multiply 2 radicals together. Again, you could do this a couple of ways. You could just go ahead and multiply these. 2 times 24 is 48, and then try to break down 48 like we just did before. Or the other thing, you know, follow the prime factors situation and leave this as 2, and then square root of 24 could be what, 4 and 6. And then you'd say, oh, well, square root of 4, there's a perfect square right there, but 6 could also break down into 2 times 3. And if you look at this now, I mean, if we really wanted to, I guess we could break that into 2 square root of 2's again. So you notice, what do we have? Square root of 2 and a square root of 2. There's a date. That comes out as a regular 2. Square root of 2, square root of 2. That's a date. Comes out as a regular 2. And then square root of 3 was left over. And so if they're outside, they can multiply together. So 2 times 2 is 4. 4 square root of 3. And if you looked up here at the original 48, you could have made that square root of 16 times the square root of 3, and then the square root of 16, oh, well, that's 4, and guess what we end up with? Same thing. All right, how about this? Well, let's see, 35 could break down into square root of 5 and 7, and then, oh, we got a date. So that means they get to come out together as a regular 5, and 7 has to stay home. And that stays under the radical, so 5 square root of 7. All right, this is where it gets a little bit tricky. Simplifying a radical with variables. Okay, this is what I'm going to look at here, but I want to give you an example with real numbers to show you how this works. Remember how I just talked a few minutes ago that if you raise something to the second power, it'll cancel the square root. So if you think of it this way, you go, oh, that square root cancels the square root. The square cancels the square root, and you end up with 3, right? Okay, that makes sense. You know, if you think about it, oh, 3, what's 3 squared? Well, 3 squared would be 9, and so then you could say, oh, the square root of 9 would be same thing, 3. You go, okay, I can see how that could work both ways. But now, so what happens here is a kind of the same thing happens. We can't take x and square it to get 9 like we did with the 3, but we can let the square cancel the square root, and so you would think, okay, following that pattern, this is going to be x. Okay. Now, there's one problem, and this is the only time it's a problem. The rest of the time, it's actually okay. Think about this. I used a positive 3 here, but what if I would have used a negative 3? what if my x, so to speak, was -3? Well, if I were going to really work this out, -3 squared would be 9. I'd have the square root of 9, which would equal 3. 3 would be my answer here, doing it the way I'm supposed to. But if I just canceled out the square and the square root, what do I end up with? I would end up with -3. Because if these canceled out, I would just have a -3. So you're like, hey, these are not the same thing. So in order for this procedure to work where the square cancels the square root, in the end, what you have to do is you have to have a positive number. So because you can't end up with a negative. So what we have to do is whenever you see this, in order to make this work, we have to put absolute values around that x. And here's the only, and how do you know when to do that? Well, when you do that is this. There's a little saying called even, odd. All right, when the root that you have is even, and of course, with square root, we don't have a number written in here, but when you get into cubed roots and fourth roots, there's numbers written here, but this, it's not written, but it counts as a little 2 in here. So whenever you have a square root, that's an even number. That's this first one. Then the power there is 2, which is even. And when you finish up at the end, this is really x to the first power. That's an odd. So whenever you have an even, odd, you have to put absolute values around that to make that work. If it ends up even, like if this was x squared, like let's say I had, well, this is beyond the square roots, but what if I had x, let's see, the fourth root of x to the fourth. And we go, oh, the fourth root cancels the fourth power. Oops, hey, wait a minute. Let's do this differently. I just want to keep that as, oops, sorry. Keep that as square root. This is really a square root. I might be getting ahead of myself here on this because I was going to talk about this in the next slide, but what happens here is if you have x to the fourth and it's the square root like this, the simple way to do it is you notice they canceled, but really what happens here is we've got the square root of, we can think of this as the square root of x squared times the square root of x squared, right? X squared times x squared is x to the fourth. So we've really got this twice, which means we now have x times x, which we end up with x squared. Kind of simple way to think about that, though, is the way I always do it is I take this number here, 4 divided by 2 is x squared. But you notice here in this situation, what happened was we had even, and we ended up with an even. So we don't really need this absolute value now, because if this would have been a negative number, if x would have been a negative number, like here, we would have squared it here in our answer, and it would have become positive again anyway. All right, well, I don't want to take any more time talking about that because we could go on and on for that. I just wanted to show you that, but let's take a look at a couple of quick examples here, and then we'll talk about geometric mean. In this situation, let's break these all up separately. So I got the square root of 45, square root of a to the fourth, square root of b to the fifth, square root of c to the sixth. Okay, so I can split these all up separately and then simplify them. So 45 would be, we could go square root of 9 times square root of 5, and then square root of 9 is 3. So we go, oh, we got 3 times the square root of 5. We simplified that. I just did this example just like this. And so again, remember, you can take the exponent out here and divide it by whatever number is here. In this case, remember, if it's a square root, it counts as 2. So 4 divided by 2 is 2, so a squared. Ooh, now what's going to happen here? This doesn't divide evenly, 5 divided by 2. So what we can do is split this up again, go square root of b to the fourth, because that's even, right? 4 divided by 2 would be 2. But we have a 1b left over. If we used up 4 of our b's, we've got 1 left over. Or the b to the first, or just square root of b. So that's like the one that didn't get a date and couldn't come out of the house. And then finally here, this would be 6 divided by 2, so c to the third. And so then what we do is we just kind of combine all the ones that we've got, put the ones that are outside of the radical first, and then the ones under the radical last. So I've got 3 a squared, b squared, c to the third, and then square root of 5b. Now the only thing we got to take a look at, let's just make sure, remember our even, odd deal. So remember even, odd. Let's see what we got here. So we know our first one's going to be even every time because it's a 2, right? So let's look at our first situation where we had a to the fourth. Even 4. It ended up with 2, even. Nope, that's okay. We don't have to worry. With the b, well, we did even and then odd. B to the fifth was odd, so we don't have to worry about that. And then lastly, the c to the sixth, well, we had even, and then 6 was even, and we ended up with, odd. So we have to put absolute values around the c to the third to make that totally correct. And so that would be our final answer there. Okay? One more like that. Square root of 32, square root of m squared, square root of n squared, square root of c. Split them up separately. 32, I'm going to go with 16 and 2 because square root of 16 is 4. Square root of m squared, they'll cancel and just give us m, right? So m, and here same thing, but just give us n. And the c, that can't do anything because it won't work there. There's no date. All right, let's put everything together. So I got 4 m n square root of 2c. Are any of those even, odd? Well, again, it starts even and even for m, and it ends up m to the first. Oh, yeah, that's one of them. And then even on n squared, and it ends up odd. So we have to put both the m and the n inside those absolute values. Okay? All right. Let's finish this up here now talking about the geometric mean. Why did we talk about all that simplifying stuff? Because the geometric mean deals with this square root, okay? And so we want to be able to simplify the square root. The geometric mean basically is a situation where we've been talking about proportions. The geometric mean is a situation that comes out when you have a proportion where the number that's on the bottom of the first one is the same as the number on the second one. So in other words, I don't know if you remember that or not, but these two here, remember, were called the means. So the x and the x were the means, and then remember b and a there were the extremes. Remember that, means and extremes. And so when you have the geometric mean, you have this situation where you have the same thing on the bottom and the same thing on the top. And so when you cross multiply, you end up with this that they have here. I'm going to rewrite it as x squared. X times x is x squared. A times b is ab. And so that was multiplying the a times b here. And then to get x by itself, to find out what x would be, to find out that number, remember, if you have something squared, to undo it, you take the square root. So we have x equals the square root of ab. So this is the formula, so to speak, for the geometric mean. So if you're ever trying to find the geometric mean, or what x is, you just take the two numbers that you have, you multiply them together and take the square root of that. That's what the geometric mean is. That's what x is going to equal in this proportion here. And so in this situation, they gave us a little thing here, 9 and 4. So really what this meant is, it's like saying I have 9 over x equals x over 4 is kind of what they're saying there. We're trying to find 9 and 4. And so what we're going to end up doing is, let's just put it in this formula. It means that x is going to equal the square root of 9 times 4. Well, what's 9 times 4? 36. So I have the square root of 36, which just simplifies down to 6. You also could have taken square root of 9 by itself to be 3, and square root of 4 to be 2, and then 2 times 3 is 6. Let's look at an example there. Find the geometric mean between 2 and 50. Whoops. And so remember, what we're doing there, again, it's like saying 2 over x equals x over 50. So this is how we're getting this. We're just cross multiplying x times x, 2 times 50. And so remember, I'll do it kind of the long, remember that's like saying x squared equals 100. We have to take the square root. X is 10. Which is, I did that by cross multiplying there, but remember, if I can just remember that formula, x equals the square root of 2 times 50, that's all I need to do. And I can go right to the part that says x is the square root of 100, and the square root of 100 is 10. Okay? How about this one? Find the geometric mean between 3 and 12. So let's just do the formula this time. Geometric mean would be what? X would have to equal the square root of 3 times 12. Again, you could multiply those together, then take the square root, or you could take the square root of each one separately and try to simplify like we were doing here. 3 times 12 is 36, so that'll be kind of easy because square root of 36 is 6. So we got 6 again. Wow, 6 is coming up a lot this time. But one more here. This one's not going to be quite as easy. I want to put one in here that was a little harder. So again, our formula, x is the square root of 12 times 15. Okay, well, if you do 12 times 15, it's going to be 180. So we could make this square root of 180. And then try to start breaking that down. Well, that's going to be a little bit harder. I would suggest let's break down these two individually. Remember how we talked about at the beginning of the lesson? So let's say, what if I made square root of 12, I made that square root of 4 times the square root of 3. And the square root of 15, what if I made that square root of 3 times the square root of 5? And let's just see what we can match up. Well, first of all, square root of 4, this would just become 2, right? Here's a square root of 3 and another square root of 3. Guess what? It's a date. So they get to come together and get out of the house as a regular 3. So these come together as a regular 3. And square root of 5, no date. And so the square root of 5 then has to stay at home by itself. And so in the end, then we can, if they're outside, they can multiply together. So 2 times 3 is 6. So our answer here is 6 square root of 5. Okay? If, like I said, there may be times where we'll want to turn that into decimals, and of course you can just type this into your calculator, but let's try to, as much as we can, just simplify the radical. Okay? Well, that's it. Appreciate you being here. Next time we're going to talk more about the geometric mean in 8.1b. So come back, and I'll see you then. Bye.